So yeah, I thought we could talk about the kidnapped robot problem today. So kidnapped robot problem is a problem that is defined for mobile robots, where you take a robot from a known location and put it in the space somewhere where the robot doesn't know where it is, and it tries to relocalize itself to find where it is in that space. And basically, a mobile robot tries to solve a couple of problems, which is the one that is maybe the underlying question is, where am I? I don't know if there's any scope in explaining what it is. This is a toy mobile robot, and it has actuators, motors here, which would drive these wheels, and it has several sensors, such as sonar sensors here, infrared sensors here, color sensor that looks in the ceiling, because this robot was trying to find its way looking at some landmarks on the ceiling. And what this robot could try to do in its life would be to navigate to a certain location, to move around, to maybe clean up a space, and so on. And the kidnapped robot problem is when I take this robot from the known location, from the known map, and put it somewhere else, and it will need to figure out where it is in this known area. So we have several algorithms in robotics where the robot could also try to create the map while trying to localize itself. But the kidnapped robot problem can be conceptualized within a known map as well. And this is the simplest way to probably start explaining about what it is. With robotics, what we differ from AI is we really live in a very dynamic and real world. And AI and robotics have been discussed in conjunction with each other from 50s on, because robotics has been an application area of AI for quite a while, even now. But the problems that robotics focuses on are more difficult because they are more real and the constraints are more real time. So for example, if you utilize computer vision for this robot, for example, if it had cameras, you wouldn't train it, or you would train it with static images, but you wouldn't work with static images. You would work with a dynamic scene, and the robot would need to probably leverage its movement capabilities to get a better view of the scene, maybe dynamically change it, and do it in real time. So the problems of the robot is typically harder, and it is buried in with a lot of uncertainty about what it can do and what the world is about. Because the robot starts with a representation of the world, let's say a map. So in this area, because this is a two-dimensional robot, you could create the scene with certain obstacles, and it would probably use its sensors to create an obstacle map. So it would say that here are probably some obstacles. And I'm saying probably because you can't really trust anything on the robot. These sensors, they may be broken. They may, if even working properly, have uncertainty in readings. They have sensitivity, especially with these kind of cheap robots. They have range. They have limited capabilities. And the motors as well. You think, for example, I would actuate this robot, this wheel, both wheels, with the same velocity. And let's say this one wheel is actually not as large as this one, for example, and you would have a small drift. And then that would actually change how you're moving. So the robot might think that it is moving 1 meter forward, but it might be maybe drifting. And these drifts, these errors accumulate over time, which makes this localization problem a very hard one, because it needs to correct every time. So drift is one of the major problems, because when you think about programming a robot, you could maybe come up with the idea that I would just actuate the motors, I would make it draw a square, and you would expect it to draw a perfect square. However, this is a quite difficult task, because if I try to, for example, draw a square here, I would look at the paper and I would try to make it look decent. And even with my very good sensors, my actuation is not very robust, and I couldn't really draw a very solid square. But when you think of it, if I close my eyes and if I try to do the same task again, I would do even worse. So this is my attempt with the closed eyes.
That's pretty good, actually.
That's pretty good, actually. But anyways, because this is not actually fully open loop. So there's these two concepts, closed loop and open loop. In this one, I was actually correcting the motion through looking at it. So I'm having this measurement, this sensing to correct the motion. And in here, I shut down one of my sensory modalities. I didn't shut everything because I still have proprioception, where I know where my hand is in space, so I have a rough idea that I'm drawing nicely. So if you think about maybe walking around with closed eyes in a complex trajectory, you would possibly get lost. And the robot is no different because there, as I say, a lot of uncertainty in the internal system of the robot, but also within the world. If it is walking or it is driving on a sand scene, then it would drift more. If it is really slippery, it would also drift, and so on. That's why these robots are typically employed with these sensors. And in modern robotics, we try to compensate for the uncertainties of the sensing, the actuation, and the environment by merging information, by supporting information so that you leverage the extra information you acquire from your sensors, from known things in the environment to make your movement better and to eventually obtain localization, which brings us to the kidnapped robot problem. If the robot is in a complete open area with no landmarks and so on, the localization problem is very difficult. And when you think of it, if you have this massive area which is empty, like this area, for example, like this room, it has quite a lot of landmarks. It can be anywhere. So if I place this robot, for example, in here, and if it only has this distance sensors, it would probably wouldn't be able to understand whether it is here, here, here. All of them are the same information for the robot. For the specific case, because it only has these frontal sensors. If this robot has, for example, some vision system, if I did put it here, then it would see maybe certain things on the floor, and then it would know that it's probably not in this area because you don't actually expect any of these landmarks in that area. But it wouldn't be sure because you can't trust the sensor. There's still a possibility that you're seeing a black frame, but maybe your sensor is wrong, so what you're seeing is incorrect. And we incorporate that kind of information when we try to self-localize the robot.
You moved the robot several times there. How does it cope with that?
Well, it would have to move around and look. So with a single sensory measurement, it would have, for example, we actually have a nice example here. If I put my robot here, or here, or here, actually the scene looks very, very similar. So if the robot is actually here, it would probably it would say that I might be here, I might be here, or I might be here. And we do represent this through probabilities in modern robotics. So this idea of probabilistic robotics has been the dominant approach to program robots at the moment. And what we do is we use mathematical formulations, the solid statistical formulations, to refine the uncertainty so that we have a better belief about our decisions, and in this specific case, the location of the robot. So what would this robot do in this situation is, this is actually quite a textbook example. So we have our robot here, which is maybe moving in this direction, and there are 3 doors in front of it. And let's put it a little bit far away for adding more interest. And what the robot does is it actually continuously updates its belief over the state of all positions. And in the beginning, you may think that the robots have an equal probability of all locations. So we start with a uniform distribution, saying that within this positional space. It can be equally anywhere. And then it takes a measurement. Let's say this is the first step. And with the measurement, it would then have data enough to update this belief. Then you would know that it saw a door in front of it. So the belief would be updated to say that I'm probably here, here, or here. Added onto this probability distribution function through the use of 3 Gaussians and giving me this 3 peaks in the distribution showing probably where I am. And I'm not killing these probabilities of being, for example, here, because as I say, your sensor could be wrong. But this is not good enough because I still don't know where I am and I still have a lot of possibilities, so I have to refine this. And in order to refine this, I would make the robot move. And the movement actually brings in a lot of more information. This is one of the powers of the robots, that they can actually change their location. They can start gathering more information. So by moving, you actually introduce uncertainty into the motion, into the probability distribution, the belief, because your motors, your actuators, they can be wrong as well. And that information would be used to, again, collect more information through measurements. And in here, after the movement, what we do is we shift our beliefs. So this is the second step, and this is, again, the belief. And I knew that I was here, and I will be moving maybe up till this point. My probable locations will be moving 1 meter forward as well. However, these probabilities are a little bit wider than this ones because I have brought in some more uncertainty through the movement. And after this step, I'm still in the similar position where I don't know where I am. And what I would do is I would take another measurement. And this is, once again, used to update my belief. And what I saw here is, luckily I came in front of another door. So I would be once again here, because everything could have been wrong up till this point. But probably I'm not here because I have seen actually 2 doors and I trust my sensory information. So that probably I would have a better belief here. I could have been still here because there was some probability over there, and then I could have been here as well. So I'm probably in front of that door, even with 2 steps in this toy problem. But iterating these over and over, sensing and updating the belief, and then moving and updating, I would get a much better posterior belief about where I am.
And presumably adding other sensors in and more movement and different dimensions is all possible.
Yes, you can add multiple sensors especially, and they do often help as long as you can fuse the information nicely. And typically in robotics applications, we do make use of many sensors. Even in this robot, we have quite many. For example, in outdoor robotics, you can use GPS to correct some of the motions. That information is not, once again, correct. But if you're on a road, for example, you have that constraint. If you move, you would have that constraint, and that would be used to perfect your positioning. Although we all know that, for example, when we are tracing our car, the information is not always the perfect one, but it's a probabilistically good one. If the space looks very much alike, then you're kind of in trouble, because this algorithm, which uses a Bayes filter, actually uses the similarities in space. So the robot always tries to find something that can be distinguishable.
That looks like it works well for a scene that the robot has already seen. A scene that it's seen, an area that it already knows. Okay. Well, what happens if you put it somewhere it's not seen before?
Well, in that case, it would need to create the map as well, and that is done through this SLAM algorithm typically, which is simultaneous localization and mapping. So it would gather the information to create the map as well as to localize itself. So it would wander around the environment and would try to eventually find a space, a location that can close the loop and say that, oh, I've been here before, so this is how the map should be. So at every step, it actually fixes the map a little bit.
Cool. Slime algorithm sounds like another video.
Yeah, probably.
Char is a bit like a hash function in the sense that it takes a block of data and it mixes it up and it uses that for its key stream. So we have a block and we'll talk about what goes in there in a moment.
So this was created by Van Jacobson, one of the great creators of the internet. He's one of the men who made the internet work and helped in the